function in which the variable y is not isolated in the equation. So this equation is not solved for y, and we need to get the derivative of y respect to x. A problem like this is solved using implicit differentiation. The variable y is not explicitly defined in the equation. So if you need to do that, the first thing that you need to do is just get the derivative both sides of the equation. For example, here say 3x squared. The derivative of 3x squared will be 3 multiplied by the derivative of x squared, that is 2x. So it will be 3 times 2x will be 6x. So I can type 6x, the derivative of this. Minus the derivative of this is 5 times 3y to the power 2. Remember that the exponent is reduced. But if you do that, 5 will be 5 times 3, 15y squared. But anytime that you get the derivative respect to a variable that is not the independent variable, in this case is y, is not the independent variable, this is a dependent variable, you need to use the chain rule. So you need to multiply by the derivative of the inner function. So let's do it. Will be 5 times 3, 15, will be minus 15y squared. Multiply by the inner function derivative, the derivative of the inner function, and the inner function is y. So anytime that you have a dependent variable, you need to multiply by the derivative of this dependent variable respect to x, that is the independent variable. Okay, so that was the derivative this side. At the other side will be 2, the derivative equal, the derivative of 2x is 2, and that's it, because this is the independent variable, so the derivative of 2x is just 2. Remember, the derivative of x is 1, so it will be 2 multiplied by 1, so it will be 2. Plus the derivative of y, so this is just a variable, y, the derivative of a variable is 1. But in this case, it's not the independent variable, you need to multiply by the inner function derivative. Okay, the derivative of y is the derivative of y respect to x. So it will be plus the derivative of y respect to x. Oh, just noticing that this is y, you need to get the derivative, that will be the derivative of y respect to x. This is the first step when you're using implicit differentiation. After that, what you need to do is just solve the equation for the derivative that you are looking for. And you're looking for the y dx. So just solve this equation, the y dx. And solving this equation, you get 6x. You can type every value, every term that doesn't have the derivative one side. This 15y squared, the y dx, can be written at the other side positive, so you can add both sides 15y squared dy dx. So you can type the equal signs, and the other side 15y squared dy dx. These two, it will be at this side, it will be minus 2 because it doesn't have the derivative. So I'm going to type minus 2 and plus dy dx, plus dy dx. So you type O for solving for dy dx. What you need to do is to type dy dx, all the terms that have this derivative at one side of the equation. And then just notice that in these two terms, dy dx will be a common factor. So just get this dy dx as a common factor, and we'll have then 6x minus 2 equal 15 dy dx that multiply 15y squared plus 1. And you get a common factor, yeah? 15y squared plus 1 multiply dy dx. And just now you need to divide by 15y squared plus 1 both sides. So you obtain that dy dx is 6x minus 2 divided by 15y squared plus 1. And in this case, you get the derivative respect to y, respect to x of y, even if the equation was not solved for y at the beginning. This is an example of use of implicit differentiation to compute dy dx, to compute the derivative of a function. Let's solve another example of the use of implicit differentiation to get the derivative of a function. Again, here we have an equation in which the dependent variable y is not isolated in one side of the equation. So this equation is not solved for y. And we need to compute the derivative of y in respect to x. So we need to use implicit differentiation. We are going to, as a first step, we are going to get the derivative both sides of the equation. And to get the derivative, you are going to get the derivative term by term in the equation. So I'm going to get the derivative of the first one. This will be 2, a value, a constant multiplying a function. So it will be 2 multiplying the derivative of this function. The derivative of e to the power something. The derivative of e to a variable is e to the variable multiplied by the inner function derivative, the derivative of the inner function. So it will be 2, because this is a constant, 2 multiplied by e to the power that we have, multiplied by the derivative of the power. Remember, we need to use the chain rule here. So it will be, and the derivative of 2x plus 1 is 2. Derivative of 2x is 2. The derivative of 1 is 0. So it will be 2 e to the power 2x plus 1 multiplying by 2. This 2 is the inner function derivative, the derivative of the inner function here. So this is like e to the power u. The derivative of e to the power u is e to the power u multiplying by the derivative of u. Derivative of u respect to x is 2. Okay, plus now the derivative of the second term, the derivative of 3 and a variable 3 will be 3 multiplied by the inner function derivative. Remember, because this y is not the independent variable, we are not getting the derivative respect to y, we are getting the derivative respect to x. So it will be the 3 multiplied by the y dx. It will be, I'm going to type plus 3 multiplied by the y dx. Anytime that we have a term, when we have a y, so we get the derivative and multiply by the y dx. You can also think in this way. You are getting the derivative of 3y. The derivative of 3y, it will be a constant 3 multiplied by the derivative of the function, the derivative of y respect to x. And this will be equal, again here we have a term with y, so it will be equal, it's like e to the power u, so the derivative of e to the power u is e to the power u multiplied by the derivative of u. So in this case, no u is y, so it will be equal e to the power y multiplied by the derivative of y respect to x. Plus, now here we have x, a term of the independent variable. So it will be here 7 that multiply the derivative of x squared. The derivative of x squared is 2x. So we have here 7 times 2x. Or we can type immediately 14x. Okay, so here, for example, 2 and 2 multiply. This is 4 e to the power 2x plus 1. Here is 3 dy dx. Here we have equal ey dy dx. And here we have 14x. The first step is just getting the derivative both sides. And the second step will be solve the equation for the derivative you are looking for. And you are looking for the derivative of y respect to x. So all the terms that have this derivative one side of the equation. So we can type this 4e to the power 2x plus 1. We can type it at the other side, negative. We are going to type the term with the y dx at the left side. So we have this 3 dy dx. I'm going to type here 3 dy dx equal ey dy dx, because I'm going to type all the terms with the y dx on the left side. So I'm going to type here minus, this is positive, I'm going to it's going to change the side of the equation. I'm going to type it minus ey dy dx plus 14x. And then I notice that the y dx will be, because I move all the terms with the y dx to one side, so the y dx will be always a common factor. and it will be a common factor, 3 minus e to the power y, that multiply dy dx. So I get dy dx as a common factor outside of the bracket, and inside the bracket remains 3 and minus e to the power y. At the other side we have equal minus 4e to the power 2x plus 1 plus 14x. And then I can type that dy dx equal 14x minus 4e to the power 2x plus 1 over 3 minus e to the power y. You can type it in this way, or you can type it in this way, just multiplying by minus 1 both sides. Yeah? So it will be 4e to the power 2x plus 1 minus 14x, and the other at the bottom will be e to the power y minus 3. These two things are the same. I just multiply by minus 1 both numerator and denominator, and obviously the answer will be the same. Okay, that finished this second example of use of implicit differentiation. Remember, first differentiate both sides of the equation, taking into account to use the chain rule anytime a term in which the variable y appears. And obviously, if there are situations in which you need to use again the chain rule, because it's a composite function of x. So in this case, e is not e to the power x, it's e to the power a function of x. So here you need to use the chain rule. This is the first step. Differentiate both sides of the equation, taking into account to use the chain rule anytime that you find a term with y. And second, solve for dy dx. Solve for the derivative that you are looking for. You were looking for dy dx, so solve for dy dx, the equation that you obtain. In this case, we have only two variables, so dy dx is the derivative that you're looking for. It will be situations in which you have more than two variables. You work exactly the same. You solve for the derivative you are looking for at the end. Okay, so that's solve this second problem of implicit differentiation. I hope you have found it useful. Thank you.